Welcome everyone. Today we shall discuss the linearity property of discrete Fourier transforms. Linearity property of DFT. Simply we can explain it as the DFT behaves like a perfect linear machine. If you want to give it a combination of a signals, it gives you a same combination of the DFTs. Let us consider if you have two signals x1 of n and x2 of n, and you make a new signal by x of n is equal to a into x1 of n plus b into x2 of n. So DFT of this x of n will be x of k is equal to a into x1 of k plus b into x2 of k. That means add the signals in time domain, their spectra will add in the frequency. So scale the signal in the time domain and the DFT, its spectra scales the signals in the frequency domain. So linearity property allows you to break the complex signals into simpler ones. Find the DFT easily using known transforms. Understand the frequency domain addition is equal to time domain addition. This property makes the DFT easy to use in filtering, convolution and signal decomposition. So let us consider a real life analogy to understand it better. Imagine the DFT as a sound analyzer that splits the audio into notes or the frequencies. If one person sings, you get a frequency of that person. If two people sing together, the analyzer just adds the two frequency patterns, and if one person sings louder, the analyzer shows bigger magnitude. So let us consider here, if here we are taking two signals or the two sequences x1 of t and x1 of k and x2 of k. So x1 of k and x2 of k are the DFT of x1 of n and x2 of n. If we apply DFT to x1 of n, we'll get x1 of k. If we apply DFT to x2 of n, we get x2 of k. We multiply by scaling factors a1 and a2. At the output, scaling factors should reflect with a DFT. When you apply scaling factors a1 and a2 to the input signals, and when you take the DFT of the whole, that scaling factors should reflect in the output, that is the DFT output of the input signals. Now let us go for the proof of the property. So here, as by the definition we know, DFT of x of n is equal to summation of n is equal to 0 to n minus 1 x of n into e to the power of minus j 2 pi by n k n, where the k exists from 0 to n minus 1. So applying the DFT of a1 x1 of n plus a2 x2 of n is equal to summation of n is equal to 0 to n minus 1 a1 x1 of n plus a2 x2 of n into e to the power of minus j 2 pi n kn. Splitting the summation on the right hand side, we get summation of n is equal to 0 to n minus 1 a1 x1 of n into e to the power of minus j 2 pi by n kn plus summation of n is equal to 0 to n minus 1 a2 x2 of n e to the power of minus j 2 pi n 2 pi by n into kn. Since a1 and a2 are the constants, we will take it outside of the summation. So if you take a1 outside of the summation of the first term and a2 from outside of the summation of the second term, here you can recognize this is the definition of the DFT of x1 of n. That is, it is the DFT of x1 of k, and this is also the definition of the DFT. It is DFT of x2 of k. So summarizing it as a1 into x1 of k plus a2 into x2 of k. So hence it is proved that DFT of the input signals with a scaling factor will reflect in the frequency response, and the DFT output, the input scaling factors will be reflected in the output. So this is the full property which we have proved. So copy it. It is very simple, and it will be given in the examination for about 5 to 6 marks. Thank you.